So now we know how to build a universe that is homogeneous and isotropic, satisfies the cosmological principle, and exhibits Hubble expansion. Now, the real universe is, of course, a complicated place full of galaxies and clusters and dust clouds, and they are moving and orbiting each other. We want a simplified model, and the simplified model is what I'm going to call dust world. In dust world, what we do is we replace all of these galaxies and clusters by a uniform distribution of matter, characterized by a mass density rho that we can adjust so that it's equal to the average mass density in our world. Is this a good approximation of our universe? Well, if you're willing to ignore little details like galaxies and clusters, yes it is. Remember that at distances above about 100 megaparsecs, the distribution of matter in our universe is approximately uniform. So what you have to imagine is that at smaller distances, I have ground out these galaxies down into their atoms and then scattered their atoms uniformly through the cosmos. Now, the assumption, of course, this matter is expanding, so what is at present at some distance d0 from us is at other times at a distance given by this function, the scale factor, and as usual we are going to call t equals 0 the present. The assumption that we make is that the only motion this homogeneous distribution exhibits is the expansion. In other words, there are no peculiar motions, there are no orbital motions. All of the dust is stationary relative to the Hubble flow that we described. This description of a uniform, constant everywhere mass density that moves only as part of the Hubble flow is what astronomers refer to, or cosmologists refer to, as dust. It is to be distinguished from what astronomers might refer to as dust, which is actual dust, the stuff that doesn't let us see through the Milky Way. The two are completely unrelated. This is just a simplified model of the distribution of otherwise stationary expanding matter. Now, let's see what we can learn about a universe described by this. And the first thing is, in the first clip I claimed that so long as the expansion is of this linear form characterized by the Hubble law, in fact, this expansion is consistent with preserving isotropy and homogeneity, and I want to make one nice argument. In fact, that argument that I made there was in one dimension. We described an expanding line. We live in 3 dimensions. Let's see what the 3-dimensional version of that would look like. So consider, if you will, this is our universe. I'm drawing a 2-dimensional slice, but everything is 3-dimensional. And I'm going to consider the dust occupying a shell. So I look at the dust that is at approximately a distance d0 from us now, where d0 is whatever I want it to be. And I build a shell of width w0, so a thin spherical shell. And here I've drawn this thin spherical shell. It lies at a distance d0 from our position, and it has a width or thickness w0. I don't want to use t for thickness for obvious reasons. Now, this is where the shell is now. Of course, if I look down into the past, a of t was smaller, the shell was closer to us. The point is that at time t, this inner version of the shell is the position of exactly the same dust flakes. In other words, since the motion of the dust is only the expansion, then exactly the dust that used to occupy this shell at some time t in the past currently is scattered uniformly over this shell at the present. And let's see what we can learn from that. So what can I do? I want to compute the mass of all of the dust that is contained in this shell. And I know how to do that because I have today the mass is given by the volume today of this shell times the density today. And from our work on Olber's paradox, to which we will soon return, we know how to compute the volume of a spherical shell. If you need to, you can look it up in that homework assignment. And the volume of a thin spherical shell is 4 pi times the square of its radius times its thickness. So there we have the volume of the spherical shell today. I multiply that by rho 0. Now, I can also write the mass as the volume at time t times the density at time t. The point being that these are the same dust grains. They've moved and they now occupy a different region in space, but they have neither been created nor destroyed. And so I can write this as 4 pi d of t squared w of t squared rho of t. And I know an expression for d of t. D of t is a of t times d0. W of t is a of t times w0. So plugging that in, I find that this is 4 pi. D of t gives me a d0 squared, w of t a w0, and 2 powers, wt is not squared, 2 powers, a total of 3 powers of a of t times rho of t. And mass conservation tells me that these are the same grains of dust that are filling a different volume. So setting this equal to that, I see that everything in the world cancels. And I find that a of t cubed is equal times rho of t is equal to rho 0. Now, we'll write that out cleanly in a moment, but notice that what I found is that rho of t is some function of t times rho 0, and in particular it is independent of r, of d. So what that means is that in every shell, the mass density is changing, but it is changing in the same way in every shell. This reinforces my claim that this expansion about some fixed point, despite the fact that it doesn't look like it's preserving homogeneity, it looks like I picked a point to expand around. In fact, in an infinite universe, it does preserve homogeneity. All of the shells are diluting at every point in space, the mass density is changing precisely in the same way, and this is a clean version of that scribble, and the conclusion is, not surprisingly, that if all distances in space grow by a factor of 2, but you have the same amount of dust, then the same amount of dust occupying 8 times the volume exhibits a mass density 8 times smaller. What other consequences can we draw from this uniform expansion of space? Well, imagine that here is our shell in the present, here is our shell in the past, and lying in that shell is an object, say a galaxy or a galaxy cluster, and we are observing this object. Now, of course, because there is a finite time of that it takes light to get here, we can't see the shell as it is today. We, sitting here today, see the shell as it was at some time in the past, long enough for light to have reached here. So let's imagine that this is where the cluster was at a time such that light from the cluster at that position is reaching us right about now. So the cluster, we see everything as it was in the past. And now in particular, imagine that we were to try to measure the size of this cluster of galaxies by using the small angle formulas. So we would look at light rays reaching us from the two sides of the object as they were at the time. We would measure the angle between them, and we would use our friend the small angle formula, which would remind us that alpha divided by 206,265 arc seconds. We can see here from the geometry, this is given by d, if d is the size of our cluster, divided by the distance, but the distance here is a of t emission times d0. Again, t emission lies in the past, so a of t is smaller than 1. This is a distance smaller than d0. In fact, if we measure the redshift, then we know that 1 over a is the same as 1 plus z, so I can write this as d times 1 plus z over d0. And let's write that more cleanly. And what we see is that if we didn't know about this game, and we thought that we were measuring angles at distance d0, we would in fact be describing this object as being much larger than it in fact is. This is the meaning of the funny title of the slide. We define a distance, a notion of distance called the angular distance, as the distance which, if inserted in the small angle formula, makes the small angle formula work with the actual size of the object. And by comparing these two, we see that the angular distance is related to the actual distance today by this expression. The angular distance is smaller, since z is always positive, than the actual distance. Objects are smaller than they appear. That's one way we use distances in astronomy. It's very important to know this. There was another use we made of astronomy, of distance, and that was in our brightness-luminosity relation. How does that work out in an expanding universe? Well, let's see. We are going to imagine this time that the object is lying at the center and we moving away from it. Why? We discussed this when we tried to figure out how far away from an object the light it emitted a while ago is. It's more symmetric to put the source in the center. Since everything is homogeneous, I can pick this however I want. And so I'm imagining that we are viewing the object from a distance d0 today, but of course when the light was emitted, we were closer. So this is a beam of light from the object to our current position. It left the object sometime in the past, and while it was traveling to catch up with us, we made our distance from our way from here to here. Good. So now I set out to describe the apparent brightness that we will see. Now, of course, the object has a luminosity L, and our brightness luminosity formula tells us that since the light is scattered, note, on a sphere in 3 dimensions of radius d0, we would expect the brightness to be the luminosity divided by 4 pi, by the area of that sphere, which is 4 pi d0 squared. This misses something. It misses, for one thing, the fact that, remember that photons emitted by the object at time t will arrive redshifted with a lambda when we observe them, that is the wavelength with which they were emitted, times 1 plus z. This is the cosmological redshift. Every photon will be redshifted. Now, the energy that a photon carries is h times its frequency, or hc divided by lambda. So we see that when a photon is redshifted, its energy decreases. We talked about this. In an expanding universe, photons are always traveling uphill, essentially, and they're forever being redshifted. And so this means that each photon brings a factor of 1 over 1 plus z less energy than when it was emitted. That's not all. It is also true that L is the amount of energy the object produces in a second, but because we are moving away, the time between when we receive signals at the beginning of that second and the time when we receive signals at the end of the second is longer than a second. In other words, the clock by which L is measured is redshifted by the same factor as gravitationally redshifted any other time measurement. The clock at the bottom of the building runs slow, giving us yet another factor of 1 plus z. If you want, you can think of it as each photon being redshifted, and the rate at which photons arrive is redshifted. So collecting these together, we find that, in fact, the brightness we observe is the luminosity intrinsically of the object, divided by 4 pi d0 squared times 1 plus z squared. And we define a distance, a notion of distance, called the luminosity distance, which satisfies the brightness-luminosity relation. And we see that the brightness distance, the luminosity distance, is not the same as the angular distance. In fact, the luminosity distance, equating these two, is d0 times 1 plus z. It's larger than the actual physical distance. Objects appear dimmer when they are far away because of the redshift. And, in fact, is related to the angular distance by this relation. And so the angular distance is less than the current present distance d0. The luminosity distance is larger, both by a factor of 1 plus z. This brings up an important question. If the light coming from a star, say, that is distant, is redshifted, what happens to the blackbody spectrum? Of course, each photon is individually redshifted. They all appear to be redder than they were, so we would naturally guess, if we looked at the object, that it looks cooler than it was. But does it even look like a blackbody? I mean, if you take the blackbody spectrum and stretch it and move it in random ways, it would not look like a blackbody. It is a wonderful property, and not coincidental, that we won't prove, of the Planck spectrum of an actual physical blackbody, that if you scale all the wavelengths, if you shift all the wavelengths by a common factor, not by a common additive shift, then the spectrum of the blackbody with temperature T becomes the spectrum of another blackbody. Given that, of course, we can tell what the new temperature will be, because you remember that just looking at the wavelength of maximum emission, Wien's law tells us that this is B divided by T, and if lambda becomes multiplied by 1 plus z, so stretched to the red, this becomes multiplied by 1 plus z, so this will correspond to a temperature that is smaller, cooler, redder, by a factor of 1 plus z, and this is indeed true. The red-shifted spectrum of a blackbody looks like the spectrum of a blackbody with this factor inserted in the temperature. So this is what things look like in universe that is expanding. Now, can this happen within Newtonian gravity?